everybody, and thank you for joining our presentation today. So I'm Valerie Zermatten, and here is my colleague Limi. We are from the Earth Observation Lab at EPFL on the Sion campus. And today we are going to talk about a vision language model for remote sensing data. So the purpose of this talk is to give you a general view on why it makes sense to use language with Earth observation data, and also to present you some application or downstream task. So the talk will be about 15 minutes, and then we will have about 5 minutes for questions. So as a quick introduction about our lab, we are, so both of us are PhD students working with Davis Tuya, and we work with Earth observation data that we analyze with machine learning, and we use data from different sensors, from smartphone, satellite, plane, etc. And we use them to target some environmental topics, such as detecting plastic on the ocean, coral reef monitoring, forest monitoring, etc. You can find more detail about our team on the website. And Lee and I are working more specially on vision language model for remote sensing. So you may ask, why do you need text? So as you know, as Cyprian just mentioned, we have an enormous amount of Earth observation data that are produced every day, and they can be used to study human activity, but also natural events almost in real time on the entire planet. So it's an incredible source of information. However, there are still important technical barriers to reach those information, and we hope that for non-technical people, it's difficult to use those data. So by using language, we hope to relieve those barriers and to make the access to those information easier for non-technical people. Moreover, we see language as a unifying modality. So if we can talk with the model, we can tell him what we need, and thus the model can be used for several applications, several downstream tasks. So to build such a model, we need several components. So first, we need a component that really understands the image and the content. Moreover, we need a part that understands human language and connect them to each other. So we need something to learn the land cover in the image. But we also want to go beyond the simple land cover, and we want to integrate general knowledge in our model so that the model knows that when we are looking for a place where to go fishing, we are looking at maybe water body, lake, river, etc. And there are several downstream tasks for vision language model that are commonly defined. So, for example, the most common one is probably visual question answering. So given a remote sensing image and some text, the model is able to answer a question. We also have, Voilà, it's back. We also have visual question generation. So given an image, a model is able to generate a question that is specific to the image and that is also more creative than a template-based question. On the second column, we have topic. We have a task where the output is a visual. So for example, we have text-image retrieval. So given a large database of images, we can build models that are able to retrieve the image that best match a query. And last, we have text-guided image segmentation. So given a text query, the model is able to highlight the matching pixels. So due to time constraint, today we are going to only talk about the last two topics. And now let's start with text-guided image segmentation. So as I mentioned earlier, text-guided image segmentation has some similarity with traditional land cover mapping. So the idea is to highlight some part of the image given some input land cover. However, in traditional semantic segmentation tasks, land cover are learned as exclusive. There are no notion of similarity between the classes. So as you can see on the picture on the left, those are classes actually from Swiss Topo, the national mapping agency. And there are several labels describing forests, such as bush forest, forest, sparse forest. But for the model, if we feed it with those labels, they will be completely different. The model will need to learn to make the difference between them. So by using language, we want a model that understands the semantic beyond each land cover classes and understands those similarities between the topics. Moreover, we want a model that is able to understand human languages. And so for this task, we built a model last year, and we presented this work at a conference. We took inspiration from the CLIP model. I'm sure many of you are familiar with it. So we use a dual encoder model with, I have this. Is it? Oh. Okay. So we have a visual encoder that extracts pattern from the image. It can be a CNN or a transformer. And for each pixel, we extract one vector. And this vector contains some semantic information. For the text encoder, we have traditional land cover label that we encode with a text encoder that is based on transformers, such as the clip text encoder or sentence BERT, for example. And we also use some text augmentation to make our model aware of a larger vocabulary. And then we use a contrastive learning approach, so similar to the one used in CLIP, to match the modality, so to learn an alignment between the text and the visual feature. So with such a model, we are able to interact with the image at the pixel level by simply computing a similarity value for each pixel with the text query. So here you can see some example of output. We have interaction with words such as vegetation, road, residential area that are a typical word for land cover mapping or remote sensing, but those words were never seen during training, for instance. Then on the second line, we have words that are not related to land cover mapping, but our model is still able to highlight the correct pixel. So before we move on, let's catch up on this first part. So with text-guided image segmentation, we build a model that is able to create maps based on the specific need of the user. We can interact with it with open vocabulary, and we obtain spatial results. On the downside, we have a model that understands open vocabulary, but it's not open word yet. That means that the model can understand any human language, so words, but it will connect them to visual concepts seen during training, so it's not able to recognize a volcano, for example, if it was not seen during training. Now, let's move on to the second part with my colleague, Limi.
So, as we can see in the previous slides, in most of the cases, we assume that we know the question in advance. We know our interest in advance. However, it's not usually the case, especially when we are facing tons of thousands of images in the archive. Sometimes we don't know where to look at. As one possible solution, VQG is a way to obtain useful information from the images. The aim of the task is to ask a question about the image content. However, as you can see in the example, the questions in the current data sets are usually too generic. So they are valid, but they can be asked to many images. For example, a typical question about the boat is, are there boats in the images? So we want to enrich the knowledge content to obtain more useful information from the large image archive. So to do that, we propose a task to generate knowledge-aware questions. The knowledge-aware questions want to ground the question in the image as well as add the common sense into the knowledge part. For example, also for the boat, the question can be asked, what is on the water and parked beside the bridge? So to do that, we are facing challenges on both data and the methodology part. For the data, we don't have the annotations. So we made 600 image question pair based on the image captioning data sets of remote sensing using knowledge triplet from ConceptNet. For example, the ConceptNet is a common sense knowledge graph, contains of many common sense concepts you can see in the daily life. For example, boat on water. Those are the typical triplet in the common sense knowledge graph. And you can transfer it in a sentence like boat is on the water. So we use this sentence to manually annotate questions for the images. As you can see in the figure, like compared to the current image question data set, the average length of the proposed data set is on average longer. So the data is ready. We have a data set that contains the knowledge triplet and also can be grounded to the image. And then we need a method that can meet the following requirement. So first, of course, we want to incorporate knowledge sentences into the whole pipeline and generate knowledge-enriched questions. So we add a text encoder into the whole question generation pipeline. It's a BERT-like model, and we can input the knowledge sentences into the whole pipeline, which is the yellow part. Yes. So it's here. And then, because we are inputting the knowledge sentences, so the question can be easily guided by the text part and has nothing to do with the image content. So to better ground the question to the image content, to ensure the certain connection between the question and the image content, we also add the image captioning as an intermediate task to ensure there's certain degree of grounding. And finally, we need to adopt the model to the limited data annotations. So in response, we proposed a 3-stage training pipeline. So we first train the vision model with green background on the image caption datasets to better adopt the vision part to remote sensing field. And then we train the language part on a question generation task to equip the model with the ability to generate knowledge-aware questions. And then we train the whole pipeline on the limited data annotation in the remote sensing we just made. So the results show that our proposed method outperforms all the state-of-the-art question generation and visual question generation method, and can generate diverse and informative questions giving a remote sensing image. With different knowledge sentences focused on the different objects in the image, the question can be different. So as a very short summary, visual language research in remote sensing aims to interact with remote sensing image using human languages. It provides an easily accessible tool for non-technical people, and it also provides an opportunity to uniform diverse information or modalities using languages, and also incorporate common sense knowledge into image understanding. Also, as a rapid developing field, there are still some open challenges. For example, the domain adaptation of large language model to remote sensing, image grounding of those models, and the annotation quality and quantity, which we are looking forward to addressing with you together in the future. Thank you.